combinations 2. This problem states that consider a money system consisting of n coins. Each coin has a positive integer value. Your task is to calculate the number of distinct order ways you can produce a money sum x using available coins. For example, if the coins are 2, 3, 5, and the desired sum is 9, there are 3 ways: 2 plus 2 plus 5, 3 plus 3 plus 3, 2 plus 2 plus 2 plus 3. The first input line has 2 integers n and x, the number of coins and the desired sum of money. The second line has n distinct integers, c1 to cn, the value of each coin, and our job is to print that one integer, the number of ways modulo 10 raised to the 9 plus 7. And our constraint is n has to be between 1 and 100, x between 1 and 10 raised to 6, and c between 1 and 10 raised to the 6. And this example is just reiterating what we have here. So we can use a dynamic programming approach to solve this question. And in dynamic programming, we're just trying to identify small subproblems and its solution and their solutions to then return the final output that we want. So in our case, the final, how many ways that we can make the final target sum. So for each subproblem, we can identify that at value I, or at sum I, what is the number of ways that we can form it, right? So in this case, we can use a top-down approach. A top-down approach in dynamic programming is basically saying we're trying to identify our recurrence relation for the subproblems so that we can continue to keep building and building and building to the final output. So we would then also need to utilize a cache, right? So then, since we're using this this approach, we can use the previously computed solutions that we've calculated, so to continue to build up. So let's say we have let's go back to this problem, right? So if we're at like sum 9, right? Then let's say we're using coin 2, then we will have to get how many ways could we build 7, the sum 7, and then as you can see, it just boils down, right? So if we're at 7, how many ways can we build 7, right? And then since we want the total number of ways, our recurrence relation for each sum has to keep accumulating from the previous smaller sum as we choose each coin. And then for recurrence, we need a base case, right? Because how else are we going to start off the computations? And a base case is basically what is the immediate subproblem that we know the answer to. And in our case, if our cache with the length of x is called dp, then at dp of 0, so at sum 0, we know that there's only one way to make 0, which is 1, right? And then this is the recurrence relation that we're trying to use. So like I said earlier, for each coin, we're gonna go through different sums, and each sum, right, we're basically accumulating what is the number of ways that we can make this using the current coin that we're on. And in order to do that, we need the previous computed number of ways that we can form the difference between the current sum and the coin. So let's say we're at like value 4. Then this is saying, okay, how many ways, and so let's say we're at value 4 and we're choosing and we're using coin 2, then this is saying, okay, how many ways that we can form 4, given that the last coin that we picked is 2. So we do dp of 4 is equal to dp of 4. So how many like we have already accumulated so far, plus the dp of 2. And the dp of 2 would give us how many ways that we could have formed 2 given our coins. And this is basically the math that's being going on here, right? So if we have 2, 3, 5, and we're trying to, in our loop, where we can calculate dp of 2. dp of 2 would be the current value, and every value initially would be initialized to 0, aside from the base case, which is 1. So it would be 0 plus the dp of 0, which is 1. So we only have one way to make 2. Then we have dp of 4, which is 0, right? Plus the dp of 2, which we already gathered from this computation, which is 1. So we only have one way to make 4. And then this calculation will continue until we accumulated everything at our target 9. So here's the code. It's fairly short. So we have nx, we have coin, which takes the inputs, and then we initialize the cache. Our cache goes from 0 to 9, so therefore we initialize 0 times x plus 1 to get the total length of the cache. Then this is our base case. dp of 0 is equal to 1. And here is the code. For each coin, so we're emulating picking each coin, right? For each coin, we have a range of its value to the target sum. This is so that we can eliminate unnecessary computations of, let's say we're at 2, then we don't have to computate 1 or 0, and then this would eliminate our need to address out of bounds issues as well. And then this is the recurrence relation here. We have dp of I is equal to dp of I plus the number of ways that we found to make our previous sum, given that the current coin that we're working on is C. And then we basically modulo from 10 raised to 9 plus 7. And then at the end, it's all going to build up to x, our target. So we just print dp of x, and that would be our solution. So in the end, what we did is we used a top-down approach using a cache to build solutions to each subproblem, to each sub-difference, so that we can find the total number of ways we can form, using those differences and the solutions to form the final value.